So I'm glad most of you made it back from the break, and it's hard to compete with the good weather, but I'll try. So I'm going to try to continue from where I left off in the last lecture. So the last lecture hopefully gave you an introduction to this area of quantum optomechanics and told you a little bit about the physics of these systems. Again, a fabric pro cavity with a movable mirror being the canonical version of these systems. Told you a bit about these systems in the simplest of all regimes, where we can really think of their dynamics in terms of a linearized theory. So the first thing I want to do in today's lecture is finish off the things I didn't get to last lecture. So finish off this discussion of cavity cooling, tell you a little bit about some of the interesting physics that occurs when you reach this regime of many photons from coupling. And then the remainder of the lecture, I really want to focus on something we completely ignored in the first lecture, something that's a really big part of these systems, the quantum measurement aspect of these systems. The fact that these systems give you a way of making position measurements as well as quantum mechanics allows. So a big thing I want to try to help you understand, how do we really think about quantum limits on continuous position detection? And I'll give you a treatment of that question or that problem that is actually very general. It's a general way to think about quantum limits on amplification and detection. And again, if you want many more details about the things that I'm telling you about, there's this sort of monster of a Reviews of Modern Physics article that took us, I don't know, 4 or 5 years to write, where there's more details than you could ever hope to sort of master yourself. All right, so quickly, where were we the end of last lecture? Here's the schematic of our system. We're driving the cavity with laser light. There's some detuning delta. Here's our basic optomechanical interaction. The thing that I hopefully got across last lecture was, again, in this system, what happens to the mechanical resonator? Well, we understood that because of the interaction with this radiation pressure force, this force that responds to the motion of the mechanics, but with a time delay, we both get a change to the spring constant or frequency of the mechanics. That's the optical spring effect. And we also can get optical damping, an extra damping, viscous damping of the mechanical resonator. And then the idea was, well, look, if I can get damping without any extra force fluctuations, that's a way to get cooling. Okay? But then the question is, well, how do I know that there aren't any force fluctuations associated with that radiation pressure force? And again, asking, is there some force fluctuations associated with the optical damping? That's the same thing as asking, from the point of view of the mirror, how hot are the cavity photons? Okay, and the approach to answering that question, how hot are the photons in this driven cavity, as seen by the mirror, the approach I told you about was this quantum noise approach. So the idea is we want to understand the quantum noise spectral density of the force that's being exerted on this moving mirror. And that force in this Hamiltonian is just the photon number in the cavity. And if we understand that force noise spectral density, well, then the asymmetry of that force noise in frequency, the force noise at minus frequency and plus frequency, where this frequency should really be taken to be the mechanical resonance frequency, that really tells me, it gives me a measure of what is the effective temperature of those photons. Okay, so in this case, what's the force? It's just the cavity photon number fluctuations. In this case, when we're strongly driving the cavity, we linearize the dynamics, this force noise spectrum just has this simple Lorentzian form. Okay, so as a function of frequency, we have a peak at minus the detuning of the laser. Okay, that's what delta is here. And the width of that Lorentzian is just set by the damping rate kappa of the cavity. Okay, so how do I get a lot of cooling? I want that optical damping. I want this effective temperature to be really small. I want the numerator to be small, the denominator to be big, lots of noise at positive frequencies. The way we can achieve that is pick a detuning that's equal to minus the mechanical frequency, and be in a regime that, well, the so-called good cavity regime, where the mechanical frequency is much bigger than that damping rate kappa. So in that case, this is what that force noise spectral density would look like. Huge peak sitting at the mechanical resonance frequency, almost nothing at minus the mechanical resonance frequency. What is this effective temperature in that regime? Well, a nice way of expressing that is as an effective number of thermal quanta. That's what this n bar back action is. And that actually now is a small parameter. Right? It's really set by the tail of this Lorentzian, kappa over 4 times the mechanical frequency squared. Okay, Okay, so this is the regime where this cavity cooling really could cool you all the way to the ground state. The effective temperature of these photons is incredibly low, okay, approaching 0. And again, there's another way of thinking about the physics in this regime. So in this regime, the so-called resolved sideband regime, here's my cavity resonance and its density of states given by kappa. You're driving the cavity at this detuning minus omega m, this red detuned sideband. And so the idea is, where's the cooling coming from? I can really think of it in terms of Raman scattering. So if I have a process where an incident photon absorbs a phonon, it lands on this cavity resonance, there's a huge density of states, that process is going to be very large, the process where we absorb energy. The opposite process, the Stokes scattering process, where the incident photon emits a phonon, that's going to see almost no density of states whatsoever. Okay, so a completely equivalent way of thinking about this physics. Okay, so what then finally happens? How do I think about the final cooling? The way I should think about it is this moving mirror is really coupled to two different dissipative baths. The dissipative bath formed by the cavity photons, again this damping rate that is the optical damping, and then there's the intrinsic bath that the mirror is coupled to. That's what will keep it in thermal equilibrium if there was no coupling to the cavity photons at all. Okay, so I have two sources of damping, two sources of these force fluctuations. What's the final temperature of the mirror? And again, expressed as a number of quanta. It's just a linear combination of what's this effective temperature of these cavity photons that we just talked about, this n bar VA, and then what is the environment temperature, the temperature associated with these intrinsic sources of dissipation. And again, the prefactors here, this is that optical damping rate we talked about, something that gets bigger and bigger. The bigger I make this coupling, the more strongly I drive the cavity. And this is the intrinsic damping rate of the mechanics. And so again, as you drive the cavity stronger and stronger, this gamma optical gets bigger and bigger. The temperature of the mechanics tends towards this very low effective temperature of the photons. Okay, and that, in a nutshell, is the physics of cavity cooling. Okay, and again, just some nice expressions to sort of have in the, in your back pocket for this kind of physics. In this optimal regime, we've got the perfect detuning of the laser minus omega m. That mechanical frequency is much bigger than the line width of your cavity. How big is this damping rate? It just goes like this dressed, this many photon optomechanical coupling G, big G squared, divided by the cavity damping rate. And again, here's that expression for the effective temperature. Okay? Okay, so that's cavity cooling. Everything I've told you about this quantum noise approach, in some sense, we're assuming that coupling between the mirror and the cavity photons is weak. So all of this is limited to sort of weak coupling, a regime where you could use Fermi's golden rule. So big G needs to be less than kappa. I'll tell you what happens when you go beyond that in just a little bit. And again, there are all sorts of experimental concerns that, as a theorist, I've completely ignored in this discussion. Right? What about the phase noise of the laser? What about the fact that the cavity might not really be itself driven by a zero temperature laser? So some of those concerns maybe we'll hear about in the talks that will be given by the experimentalists. So I will not say anything more about that. Okay, and then again, the nice way of thinking about this physics, this kind of sideband cooling or Raman scattering picture, it's important to realize that, of course, the exact same physics occurs in other settings. This is the exact same physics that you use to cool, to sideband cool in ion traps. The same kind of physics, even in nanomechanical systems, has been explored by coupling a cantilever to some other kind of driven quantum system. Okay, and so one example on this list, a cantilever coupled to a quantum electronic device, a superconducting single electron transistor. I think we'll hear a little bit about that in Keith's talk just after this. Okay, and just to show how useful this physics really has been, here's a slide that I've taken from Florian Marquardt that at least, this is maybe already out of date, but from 6 months ago, really showed some of the state-of-the-art experiments using this physics to cool a relatively large mechanical degree of freedom. So on the x-axis here is this, the inverse of this good cavity parameter. How big is the mechanical frequency compared to the cavity damping rate? And of course, we love to be out here. the solid blue curve here is showing what's the coolest you could possibly get the mechanical resonator. The y-axis here is, again, the phonon number in the mechanical resonator. And here are these different experiments that have done this cavity cooling. Okay, so you even have experiments that are not in this good cavity regime. These experiments with these kinds of interferometers used in gravity wave detection, where again, you can really get orders of magnitude in terms of the cooling. The blue shaded region here is where you're getting into the quantum regime. The average number of phonons in the mechanical resonator is less than 1. And again, some very recent experiments that are using this physics to get into that regime. Okay? So I think that's pretty much all I wanted to say about the conventional cavity cooling physics. And again, just to make sure we're all okay with this and we didn't forget things that I told you last lecture, let me just pause here for a second. Are there questions just about what I've said here?
Yeah, I'm wondering, so the sort of way that we think about this, you've been saying, is that in the resolved sideband limit, you're able to cool, it sounds like better, but maybe it's just to the ground state, whereas here in the unresolved sideband limit, it really looks like the most significant, fractional cooling is done. Like that MIT is, on the way on the left, is tons of orders of magnitude. So does being resolved versus unresolved have little to do with your cooling power and more to do with ground state, or
so the biggest thing that this resolved sideband parameter really determines is what is the lowest temperature you can really get to. So this question that I started by sort of discussing, what is the effective temperature of this bath that is presented by the cavity photons? That really is determined by this parameter. And if I ever hope to really get close to the ground state, the thing that I'm trying to cool to is the temperature of those photons, and that better be small. And that's what this parameter controls. Okay, so even though if you start really high here, if you could really get down to this value here, which yes is much bigger than the quantum, that's still a lot of cooling. Okay, the resolved sideband parameter is really controlling this minimum possible phonon number curve. The effective temperature of the photons as seen by the mechanical resonator.
The circulating power in the MIT experiment was pretty big.
Yeah.
You wouldn't want to put your finger in there.
Okay, and just maybe one other thing I'll just quickly mention and not really go into too many details. So all this physics, I went through this quantum noise approach, but at the end of the day, you might think, well, look, this Raman scattering picture is really simple. Do we really need this quantum noise approach? One of the nice things about the quantum noise approach is you can really use it to understand how any driven quantum system acts as a thermal bath. So we can even take our cavity optomechanical system and change things just a little bit and get a slightly more bizarre kind of situation. So imagine I have this cavity optomechanical system, and imagine, as opposed to just having the cavity frequency depend on x, for some reason the damping rate of the cavity also depended on x. So in this kind of circuit system, you can imagine doing that by having the coupling capacitor that couples your cavity, your LC oscillator, to this dissipative transmission line, have that capacitor be x dependent. Okay, so in this case too, you could ask, well look, the driven cavity is still going to act like some kind of dissipative bath from a mechanical resonator. There's still going to be some force noise, there's still going to be some optical damping, right? How cold can I get? So again, the force noise, the force operator here is now not just the number of photons in the cavity. The fact that the damping rate depends on x means the force actually involves the tunneling operator that takes photons in and outside of that cavity. So we can still play these games, we can still calculate this quantum noise force spectral density as a function of frequency. And that's what this orange curve here is. This blue curve is what we had before. If we just had the usual coupling, frequency depends on x. When kappa depends on x, well, there's the spectrum. That is no longer a Lorentzian. It's a photoresonance, a line shape that comes from interference. And the interesting thing is, boom, it goes exactly to 0 at some negative frequency that you can tune. Okay, so in this system, again, you can still use exactly the same approach. The quantum noise spectral density tells me how the system acts like a dissipative bath. You can actually use interference physics to cool all the way to the ground state by putting this 0 exactly at the negative frequency of the mechanical resonator. That means, as far as the mechanics is concerned, the cavity photons look 0 temperature. With this system, you could cool to the ground state in principle without having to be sideband resolved. Okay? So again, just to give you a flavor of this approach, this quantum noise approach, is really a nice way to examine the physics of a lot of different systems, not just this canonical cavity optomechanical system. All right, so let's leave cooling aside. Let's say a couple more things about quantum optomechanics in this linearized regime before we turn to the question of quantum measurements. And so again, all of this optomechanical damping physics, how do we understand that? Well, look, this is the way my mechanical resonator responds to some external force. Here's that force susceptibility. We saw that even from the semi-classical equations, the interaction with the cavity changes the susceptibility. It gave us this self-energy, and living in this function here was the optomechanical, the optical damping. All right, well, let's flip things around, right? The mechanical resonator's susceptibility can be changed from this interaction. What about the cavity's susceptibility? Okay, so what could I ask? Well, look, here's the system we talked about. I had this strong laser drive that was giving me this many photon optomechanical coupling. Imagine now I put on a second weak laser drive, okay, a second drive on this cavity. And again, remember D is our photon lowering operator. Once we've displaced away the amplitude we get from this large driving laser. Well, now with this weak driving probe laser, we're going to get some average value for this photon operator D. And that's going to be proportional to that, the amplitude of this probe beam. And again, there's going to be some susceptibility that sits in front there, exactly like the mechanical resonator responding to a force. And if there was no interaction, optomechanical interaction, what would this factor be? Well, it's just the susceptibility of a harmonic oscillator. In this rotating frame, I have the detuning of the probe, the frequency of the probe minus the frequency of the cavity, and I have the damping rate of the cavity. And so if I just had that, this would basically just give me a Lorentzian response. Now, with the interaction with the mechanics, I'm going to get a modification, exactly like we got a modification of the mechanical resonator. Okay, so what is that going to do, right? Well, what is that self-energy of my photons look like? Again, it has exactly the same kind of form that we saw in the other case, in the mechanical case. I've specialized to a really simple regime here, where again, we're in this optimal setting for cooling. I'm driving at the red detuned resonance. Delta equals minus omega m. That's this big laser beam here. And so this self-energy, this change in the susceptibility, again, it goes as second order in this coupling G. And then I just have this factor here. Omega m is the mechanical resonance. Gamma is the damping rate of the mechanics. And so what do I have here? I have something that gets really, really big, right, when omega is equal to the mechanical resonance. Okay, and what does that mean? Well, look, if this gets really, really big, this self-energy, this whole factor here gets really, really small, D gets really, really small. So this is where this name, optomechanical induced transparency, comes from. Without the interaction with the mechanics, you put on this weak probe beam, you're going to get some photons, some extra photons in the cavity. The average value of D would be non-zero. Now with this interaction, in this very narrow range of frequencies, you can actually suppress the excitation of the cavity. And what's a way of understanding that? Well, look, so in this very kind of simplified schematic, the circle here is supposed to represent my cavity mode. The square is supposed to represent my mechanics. And so here's my incident probe laser. I could have a photon just go into the cavity mode. That's one process. But what else could happen if I have this big G? Well, the photon could come in, go into the mechanics, right? This interaction will take a photon, put it into the mechanics. So the photon could go into the mechanics, come back. That's another way to get a photon in there. Or, we could have that kind of bounce process happen twice, et cetera, et cetera, et cetera. It's the interference between all those processes that really gives rise to this modification here. Okay, and so what does that actually look like? So here I'm basically plotting what's the average value of D, this extra amplitude for photons in the cavity from this probe laser, as a function of its frequency. If there was no optomechanical interaction, big G is 0. That's just our cavity Lorentzian that we'd expect. When you turn on this interaction, here's that modification, this really, really narrow dip that's coming from this interaction with the mechanics. Okay, so the upshot of all of this, in the same way the optomechanical interaction can change the mechanical susceptibility, you can also change the cavity susceptibility. Okay? So what happens if I crank up this coupling constant even larger? So what happens at this feature here? Well now, so here I've taken big G to be bigger than kappa. That feature now starts to really look like two distinct peaks. Okay, and that also is not so surprising, right? If I'm driving the system like I am in this case, at this red detuned sideband, where basically photons and phonons have exactly the same frequency, well then the interaction that I have to worry about is just a simple interaction here, right? At a Hamiltonian, we could all diagonalize. I'm going to get new normal modes for the system, right? Normal modes that are linear combinations of a photon plus or minus a phonon. And those normal modes will be just split by twice this interaction constant G. Okay, so this EIT physics, the fact that this susceptibility is modified when we turn on the optomechanical interaction, as you crank things up, that feature really turns into something that in a sense is expected. It tells us about the presence of these normal modes. Okay, so another aspect of just the linearized optomechanical theory, if you make this interaction big enough, right, the splitting of these normal modes becomes bigger than the dissipative rates in the problem. You can really see these distinct normal modes in an experiment. Okay, and then the last aspect of this physics, well, let's go back to the cooling physics. Right? So all that quantum noise stuff I told you about required big G to be smaller than kappa. So now when big G is bigger than kappa, we have this normal mode physics. What does that do to the cooling? Okay, and the short and simple answer is basically in this equation here. So this is now telling me what is the lowest temperature I could get the mechanical resonator to if I really had a very, very large big G, a really large optomechanical coupling. Okay, and the crucial thing to notice here is there is a term that gets bigger the bigger you make big G. Okay, and why is that happening? So the upshot of all of this is having a really, really large optomechanical interaction is not good from a cooling point of view. When you actually start to resolve these normal modes, the cooling physics is actually no longer as efficient. Why is that? Well, again, here's our optomechanical interaction. You know, again, when we've made this linearization that I talked about last lecture, it's this first term that we want to use for the cooling. Right? I want to move my hot phonons into my cavity, so destroy a B, create a D. If I make G big enough, this term here that creates a phonon and a photon, even though that's not resonant, that doesn't conserve energy, that starts to be important. Okay, so the upshot of this, you make big G large enough, bigger than kappa, you start to see the physics of these two normal modes, but at the same time, your cooling actually gets worse. Okay? And that's pretty much it in terms of what I want to say about this sort of strong coupling physics. I think maybe John in his lectures will say something more about this, show some experimental data touching on this. What I want to do now is, kind of switch gears. So everything I told you up till now and in the first lecture was really focusing on the back action aspect of these systems, the fact that, look, the mechanics is modified by these radiation pressure forces, we can use that to cool. Let's now switch gears and actually focus on the quantum measurement side of things, okay, which is sometimes maybe the more obvious aspect of these systems. The fact that, look, if I actually want to measure what the mechanical resonator is doing, I can do that by monitoring the phase shift of the reflected light from the cavity. Okay, so the basic way that works, again, I'm just focusing on a perfectly one-sided cavity, so all the laser light that comes in has to come out again. What happens? Well, as this cantilever moves, it changes the frequency of the cavity. It's going to change the phase shift of the light that's reflected. Okay, and so again, for a small change in x, what's the change in phase of that reflected light? Well, here's the expression here. It's basically given by our optomechanical coupling. How strongly does the frequency of the cavity depend on x, times the position of the mechanical resonator, divided by the damping rate of the cavity. And here I'm assuming that we're driving the cavity on resonance when x is equal to 0. Okay? So the idea is that typically, look, we're interested in doing quantum position detection near quantum limits. The changes in x we're going to be interested in trying to resolve are going to be on the order of the 0-point motion, or maybe an order of magnitude bigger than that. Those changes in x are going to give rise to incredibly small phase shifts. Okay, so for typical systems, this phase shift is basically change in x divided by picometers, let's say. And again, the 0-point motions we're going to be interested in these sort of macroscopic mechanical resonators on the order of femtometers or even smaller. So the kind of measurements we're going to be talking about are going to be weak measurements. Okay, so to resolve this incredibly small phase shift, we're going to have to worry about the number-phase uncertainty relation. We're going to need many, many photons to actually be able to resolve this incredibly small phase shift. Okay, so just a little bit more about how would we really measure that change in phase. We do, or one thing we could do, is a homodyne experiment. So here's our cavity, here's that big laser we sent in on resonance. It's reflected. There's some information in the phase of that outgoing laser beam. Here's its amplitude A out that tells me about the mechanical resonator. And again, I'm always going to be interested in this talk in weak measurements, weak coupling. This change in phase is going to be small, so I can Taylor expand that. And so what I really want to measure is this change in the amplitude of the reflected laser light. And so the way to do that in this homodyne experiment is basically send that light on a beam splitter, interfere it with a classical reference beam at the same frequency. And so we interfere it on this beam splitter. We take what's coming out, send it onto a photodetector. So what we measure is basically the sum of this A out plus beta. Okay, and the interference term, if I pick the phase of beta in a property, in this case to be imaginary, is just going to involve this term here that I'm interested in. Okay, so that's the way, in principle, we can resolve this phase shift, turn this information in phase into information we get out of a photocurrent. And again, why is the measurement weak? So again, the average photocurrent is going to be proportional to what my mechanical position is doing. That's this first term here. Why is it going to be hard to resolve that? Well, certainly one reason is, even if there was no coupling to the mechanics whatsoever, there's going to be shock noise in this photocurrent. And that's what this second term here represents. So even with no mechanics, look, there's lots of noise in this photocurrent. If I have this small change in the average value I want to resolve, it's going to take some time to resolve that above the noise. Okay, so in this kind of setup, what really enforces that number-phase uncertainty relation? It's that shock noise in that photocurrent. Okay, so just to again recap, so we're interested in weak continuous measurements, just to really be concrete about that. Our mechanical resonator, of course, is not just sitting in place. It's also moving, so we can think about just the thermal Brownian motion of our mechanical resonator. Maybe it looks something like this. So we have a variance of these position fluctuations that is really set by the temperature of the mechanical resonator. And in terms of, again, how quickly does the envelope of these fast oscillations of the mechanical frequency change, that's going to be set by the damping rate of the mechanical resonator, which is big gamma here. And again, what we're trying to do is not figure out at some instant in time exactly where is the mechanical resonator. Right? That's hopeless here. What we'd rather like to do is just really follow the envelope of these oscillations. Okay, so an equivalent way of thinking about that is, if I think about writing the mechanical motion in terms of these quadrature amplitudes, so look, I know it's oscillating at the mechanical frequency, cosine of omega m, sine of omega mt. I'd like to know how the amplitudes of those two terms are changing in time. And that's something that's happening on a much slower time scale than the mechanical frequency. That's happening on a scale set by this damping rate. Okay, and again, the thing that we have to worry about, but look, these two quadrature amplitudes don't commute with one another. If I want to try to get information about both of them at the same time, I know there's got to be some kind of quantum limits involved. Okay, and so what we want to really do is try to precisely formulate what are the quantum limits on this kind of weak continuous position measurement. Okay, so the way we're going to do that is in terms of noise spectra. We're going to really characterize the good noise, the noise in the mechanical resonator that we're trying to detect, and the bad noise, all the extra noise added by the measurement. And the question is, how small can I make all that bad noise? So let's just start by just recapping how do we characterize the good noise. I just have a mechanical resonator at thermal equilibrium. How do I think about its position fluctuations? So again, for some time interval 0 to tau, I have these thermal Brownian motion fluctuations. Here's some trace x of t. We can imagine Fourier transforming that. And if I took the modulus squared of the Fourier transform, again, I get something peaked around plus the mechanical frequency minus the mechanical frequency. If we now average that over many realizations of these fluctuations, we basically get our position noise spectral density. Okay, two Lorentzians, one at plus the mechanical frequency, one at minus the mechanical frequency. And if we're in thermal equilibrium, those spectral densities are just given by the fluctuation dissipation theorem. Okay, so what does that mean? So this position noise spectral density, again in the classical limit, it's proportional to the temperature of the oscillator and to the imaginary part of this force susceptibility that we talked about. Okay, how do I deal with that in the quantum limit? Well, I basically replace kBt by h bar omega over 2 times this hyperbolic cotangent function. Okay, so that's the quantum version of the fluctuation dissipation theorem. So this is the good noise, right? This is what we think the mechanical resonator is actually doing, right? So this is what we love to see and detect in the measurement. But what do we actually see? Well, we're not going to actually see that. Okay, so what we actually see, the measured x, the thing that we extract from our homodyne current, right, from the cavity, is the actual signal that we think the oscillator is doing, plus some added noise. Okay, and the added noise of the measurement has two parts, and we want to characterize both of those. Okay, so again, here's our setup. The information on the mechanical position is going into the phase of this reflected beam, which we're then turning into a photocurrent. So that photocurrent, again, here's the nice part we like. They're telling me about the mechanical position. Here's this added noise. Okay, I'm going to rewrite this in this little way, in this way. So there's two parts to the added noise. This is the total added noise here. The first term here is, again, what I already told you about. That look, even if there was no coupling to the mechanical resonator, this photocurrent would have shock noise fluctuations in it. Okay, so that's an imprecision noise. And what I'm doing in this expression here is this imprecision noise, these shock noise fluctuations, I want to think of them as equivalent position noise fluctuations. So all I do is I just divide out by this response coefficient lambda, right? What's the coefficient that turns position into a photocurrent? And that gives me this first term here, the imprecision noise, the shock noise in the photocurrent referred back to position. So this is something that, look, if I just start cranking up the coupling between the mechanical resonator and the cavity, well, I'm going to increase this response coefficient lambda. This term will get smaller and smaller and smaller. So the imprecision noise, how do you beat that? How do you make that smaller? You just couple more and more strongly. Or equivalently in this system, just use a stronger and stronger laser drive. Okay. Yep.
Is A the same as capital G?
So A here, sorry, again, I mentioned last lecture, notational fluctuations will occur. Here's an example. A here is exactly the same as d omega cavity dx. So it's still the optomechanical coupling. Okay, so the first term, the imprecision noise, something we can make smaller and smaller by just coupling more and more strongly. The second term, right, the second term is the back action noise. So part of the position in this first term here is actually coming from the fact that, look, by coupling the mechanical resonator to the cavity, I have this new fluctuating force in the problem, which we've already talked about, the fluctuating photon number of the cavity. And that fluctuating photon number is going to give me extra position fluctuations. Okay, and those extra position fluctuations, that's the back action noise. That's an added noise from the measurement. Right? That's not something I want to detect. That's not something that would have been there if I hadn't coupled the mechanical resonator to this measurement device, to this cavity. Okay, so this is the back action noise. This is something that's going to get bigger and bigger the more and more strongly we couple our cavity to the mirror. Okay? So the question now is, well, look, we have these two noises here, right? Clearly, just making the coupling infinitely big or infinitely small is not a good thing to do, right? Because one of these noises will just kill you. So the question is, if I try to optimize things, how small can I actually make this total added noise? Okay? And so that's where the quantum limit that I'm going to tell you about comes from. If I consider both of these noises and any correlation maybe between them, how small can this total added noise of the measurement be? Okay, and the answer I'm going to tell you is basically the smallest this noise can be is exactly equal to the 0-point motion of the oscillator. And again, as we're talking about noise here, I'm going to have to make that a little bit more precise. We're going to have to talk about the noise at each frequency. At each frequency, we're going to have this constraint. Okay, so let's try to make this statement a little bit more precise. The smallest the added noise can be is equal to the 0-point noise spectral density. Okay, so if there was no added noise whatsoever, what would the noise in this homodyne current that we're measuring be? It would just be proportional to the noise that we want, the intrinsic position fluctuations of the mechanical resonator. Again, a notation fluctuation, we've gone from SXX to just SX, exactly the same thing. Okay? So if you include the noise that's added by the detector, well now we have this nice noise that we want, the good noise we wanted to have, the intrinsic noise of our mechanical resonator. Here's the added back action noise. Here's that added imprecision noise. So if we plot that, again, here's noise spectral density versus frequency. This red area is the ideal case, the intrinsic position noise of the mechanics. This term here is basically going to be a flat white noise background, so that's the imprecision noise. It just shifts all of this up. And then adding the back action, that's added position fluctuations. That's another Lorentzian like this. That gives me the full noise that's measured in the experiment. And again, the difference between this red curve and this yellow curve here, that's the added noise. So now what I can ask is at every single frequency, I can measure how different is the actual noise of the mechanics versus what I actually see. It's that difference that's the added noise of the measurement. And now the rigorous statement of the quantum limit is at each frequency, that added noise has to be bigger than the 0-point noise of the mechanics. And what do I mean by the 0-point noise of the mechanics? Well, I told you, look, in thermal equilibrium, Sx of omega is just given by the fluctuation dissipation theorem. At 0 temperature, this is the expression we're going to get out. Okay, so this is the rigorous statement of the quantum limit. We want to now understand where exactly does this come from. Yeah, question?
Yeah, I'm sorry, I guess what is the thermal and quantized? What's the quantized if it's not the imprecision or back action noise? I just got
Say that one more. What's the?
So what is the in the thermal and the quantized on the bottom? What is the quantized? Because I thought they could.
So this is everything I'm talking about here is completely independent of whether my mechanical resonator started at 0 temperature or started at some finite temperature.
Oh.
So all of that is what I'm calling the good noise. The fluctuations of my mechanical resonator that would have been there even in the absence of the coupling to the cavity. So that's this red curve here.
Okay.
It could be thermal, it could be 0 temperature noise, doesn't really matter. All I'm interested in is the stuff that's added on top of that. And that's the stuff that I'm interested in asking, how small can I make that difference? Good place to pause. Other questions? Okay. There's another thing we should worry about a little bit here, right? So look, we go back here, maybe this is not really any surprise. There's back action noise in this system. We're trying to measure position. We're going to mess up momentum. How do you mess up momentum? You kick things around in a random way. So look, for general reasons, we expect there to be back action, right? A force like that. But how do I know that I can't have these two different noise sources, the back action noise and the imprecision noise, be completely anti-correlated with one another? Right? So I could have back action noise that's non-zero, but why couldn't it just completely cancel that and have zero added noise? Okay, so the interesting statement is just knowing that you need to have back action is actually not enough to tell you that this added noise has to be non-zero. There's an additional ingredient that you actually need to tell you that, look, these two things, even if you worry about correlations, they're never going to completely cancel out. You're always going to get something that is non-zero and that at best is equal to the zero-point motion. Okay, and what is that added ingredient? Well, what we're really doing here is we're doing a measurement. We're taking these very small position fluctuations in the mechanical resonator and trying to get some big signal, this photocurrent, that we can then read out and think about classically. We're really doing amplification. Okay, taking something small, the position fluctuations, getting a big classical signal out of that. Okay, and that's the added ingredient that will actually give us this extra piece of information that makes it impossible for those two noises to be anti-correlated. And a very crude way of thinking about where this comes from, it's described in more detail in this Reviews of Modern Physics I described. How should I think about amplification in the most basic way? So imagine an amplifier where the input and the output of the amplifier are the exact same thing. So I start with an oscillator that's doing some harmonic motion. I can think of that as a point in phase space. And what does my amplifier do? It just exaggerates the amplitude of that motion, keeping the phase the same. So how should I think about that in phase space? Well, I start with some point in phase space before amplifying. After amplifying, well, it gets moved outwards radially. So what would that amplifier be doing? It would be taking some area in phase space and expanding it. Right? That'd be perfect amplification. So we know that we can't do that with Hamiltonian dynamics. Right? We know that areas in phase space can't expand from Liouville's theorem. So what's the way out? The way out is I need extra degrees of freedom in the problem. Extra degrees of freedom such that there are other regions in phase space that while this expansion is going on, I have some contraction going on in these extra degrees of freedom, such that Liouville's theorem isn't violated. Okay, so to get this kind of amplification to occur, we need extra degrees of freedom. Quantum mechanics, if we have extra degrees of freedom, there's going to be noise associated with those extra degrees of freedom. Okay? So the upshot of this, the added ingredient to really get this quantum limit that we're after, it's not just the fact that, look, back action exists. We also need the fact that there's really a measurement going on, that we're really amplifying these small position fluctuations. Okay, so let's try to make this a bit more precise, to really rigorously derive where this quantum limit comes from. So here's our detector, our optomechanical cavity again. There are the different noises we need to worry about. SI is the noise in the homodyne current, the spectral density of that noise. And again, because I'm interested in really a weak measurement, a weak coupling between the motion of this oscillator and the cavity, I'm going to be interested in knowing these different noises, these noise spectral densities, at zero coupling to the mechanics. So I want to understand the properties of my cavity before I even couple the mechanical resonator to it. So what this S bar I is going to represent, what are the fluctuations in this photocurrent when there's no coupling to the mechanics at all? Okay, and so again, this photocurrent, the fluctuating part is going to be an operator. The spectral density that we're going to be after is the spectral density that acts like a classical spectral density. I'm going to want to symmetrize or take the anti-commutator of these two operators. Okay, because again, I told you if I didn't do that, what's in the average here doesn't have to be real, because these two guys don't necessarily commute with one another. If I want the classical part of the noise, well, we throw in that anti-commutator there. Okay, so this is the intrinsic imprecision noise, or the shot noise, in this output quantity I of t. I can do the same thing for the back action noise. So F here is exactly the same as the photon number fluctuations in the cavity. And now we can also worry about, well, maybe these two noises are correlated with one another. So I can also talk about a correlation noise spectral density, defined in exactly the same way. Okay? All right, so, and again, I'm going to discuss this in a way that isn't specific to this optomechanical cavity. this discussion is going to be general enough to describe any kind of linear amplifier. Any kind of two-port linear amplifier, you're going to have some kind of back-action noise, some kind of imprecision noise, and a possible correlation. All right, so we have these three different noises. What can we say about them in general? Well, classically, we couldn't really say a whole lot. Quantum mechanically, there is something very interesting we can say. There's a kind of Heisenberg constraint on the noise properties of any system capable of acting like a detector. Okay, and so what is this Heisenberg constraint on noise? At any frequency, if I take the product of the back-action noise and this imprecision noise, and I subtract off the correlated part, right? Classically, the only constraint would be, well, what's left over, right, has to be bigger than 0. Right? The most correlated these two things can be is perfectly correlated. Well, quantum mechanics puts an extra constraint on the right-hand side. And that extra constraint says, well, look, if you actually have a detector, right, if this output quantity, this current, can respond to the motion of the mechanics, something that couples to F, well, then there's a minimum value for this difference here. Okay, so this is a quantum constraint on the noise. If you have a detector, if you have some response, right, you must have some noise. This perfect correlation is not possible. You can't have a 0 there. This is going to be an important part of getting to this quantum limit on position detection. Okay, and again, where does this come from? For a general linear system, how would you calculate that response coefficient lambda there? You could just do it using perturbation theory. The answer you would get is known as the Kubo formula. The answer you get is that response coefficient involves the commutator of these two operators. The commutator of the thing we're measuring, the Ohmsdale current in our case, the thing my signal is coupling to, that's the photon number operator in our case, the back action operator. So if I want some response, these two things can't commute at all times. If we have two operators that don't commute, we know we're going to get some kind of uncertainty principle. Here it's things that don't commute at different times. It gives us this Heisenberg constraint on noise spectral densities. Okay, so this Heisenberg uncertainty kind of constraint is coming from the usual place. Okay, so we have this constraint on quantum noise. There's something else I won't go into too much detail, just so we don't run out of time. There's also this question of, well, am I really amplifying the signal? Am I starting with something small and getting something big? So I need to define some notion of the gain of my system, the power gain of my system. Okay, and there's a way of doing that. And again, I'll just sketch it very quickly. Imagine I actually took the output of my detector, in this case the Ohmsdale current, and I used it to drive another oscillator. Okay, I just write down a term in the Hamiltonian where this second oscillator Y, it's driven by a force which is exactly I of t. Okay, so a question I could ask is, well, how much power is drawn at the input of my detector? How much energy is sucked out of my mechanical resonator? Versus how much energy is actually put into that auxiliary oscillator? And that ratio, which is dimensionless, that's a dimensionless measure of the gain or the amplification of this measurement. Okay, we're going to want to be in the regime where this gain is actually large. That's where I'm actually doing some amplification, making a small signal large. Okay, so that's another ingredient that's going to go into our derivation. And now with those pieces, so there's this Heisenberg constraint on the noise, there are additional simplifications that come from having this gain parameter being large. Now we can rigorously derive this quantum limit. Okay, there are 3 steps to reaching this quantum limit on position detection for any kind of linear detector. Okay, and we'll go through all 3 of them. The first is going to be, again, balance the contributions between back action and imprecision by not coupling too weakly or coupling too strongly. The next is really make sure you use a detector that optimizes this Heisenberg bound, right? Because you take any old system, this difference here is not going to be exactly equal to the smallest value you can have quantum mechanically. And there's this third aspect too that might seem a little stranger. You actually have to have the exact right value of this cross correlator. Let's actually see how this works. So look, my general expression for the added noise, I have my imprecision noise, the noise and the shot noise that would be there even without the mechanics. the back action noise. Okay? A nice way of thinking about that imprecision noise is just, again, delta I divided by lambda. I'm going to call that delta Z, the imprecision. And I'm keeping the coupling constant in here. So A, really think of as being the optomechanical coupling. Okay, so this first term here, the imprecision noise, it gets smaller and smaller the bigger I make the coupling. This second term here is the back action noise. So the back action noise is proportional to the coupling. It depends on how big is the back action force noise. And this chi xx, which we've seen a bunch of times now, this just tells me how does my mechanical resonator respond to that back action force? How do I turn a force into a position fluctuation? So all I do is I basically take this and I square it, and that turns this delta x into added noise, position noise spectral density. So these two terms here, I square this, that's this imprecision noise contribution. I square this, that's the back action contribution. And now I worry about the fact that these two guys could be correlated. I'm not going to just throw that away. So how do I reach the quantum limit? Well, the first thing is, look, my coupling is showing up. If I make the coupling big, the back action gets really big. Make the coupling too small, this imprecision noise gets really big. The first thing I'm going to do is pick the optimal value of A. Okay, when I pick the optimal value of A, right, the bound on these first two terms is just basically the geometric mean. Okay, so I take A to basically be the ratio of these two terms. So if you optimize this coupling constant, again, I find this expression now for what's the minimum value my added noise can be. And this is looking good, because now we see it's the product of the imprecision noise and the back action showing up. In this correlation term, I've just simplified things a little bit. What I've done is I've taken out the magnitude of this force response susceptibility, put it out front, and phi is just the phase of that susceptibility. Okay, so we optimize the coupling. What's the next thing we do? Well, now we hope and pray that we have a quantum limited detector. So what does that mean? This product here is going to be as small as is allowed by the uncertainty principle. Okay, so we go back a couple slides, we see what that inequality is. I'm going to replace this product here by its quantum limited value. Okay, and the quantum limited value is exactly what's given in this square root here. Okay? And now the last thing we need to use, and again, I've also used the fact here that the power gain of the detector is large. And that constraint basically tells me that this cross-correlation noise has to be real. Okay, so we're almost there. The last thing to do to really see how small could I make the right-hand side here, this added noise, well, now there's really no remaining constraint on how big that cross-correlator could be. Okay, so now what I'm going to do is I'm basically, so again, I'm interested in minimizing this added noise at some given frequency. So we could pick a frequency. It could be the mechanical resonance frequency. It could be detuned from the mechanical resonance frequency. When I pick a frequency, that basically picks the phase of this susceptibility. If I know that, I can pick, well, what's the optimal value of that cross-correlator? And the optimal value of that cross-correlator is determined by the cotangent of that phase. We finally use that, we plug that optimal value of what this cross-correlator should be, we finally get the answer that we expected. What's the final answer we get? When you go through all three of these steps, what's the lowest you can make this added noise at any given frequency? It's basically h bar times the imaginary part of that susceptibility. But that's exactly the spectral density of these position noise fluctuations at zero temperature. The 0 point position noise of the mechanics. Okay, so what does this tell us? It tells us that, look, there's a rigorous constraint on this added noise spectral density at every single frequency. It also tells us, in this step here, that to reach the quantum noise, the quantum limit at different frequencies, we actually have to do different things. Right? For different frequencies, I need to have different values of this cross-correlator. Okay, so the usual thing that we're interested in is, let's focus on the added noise right at the mechanical resonance frequency. In that case, the best thing to do is to have no correlations between back action and imprecision. In that case, this minimum possible added noise takes this form here. It's the 0 point motion of the oscillator squared times 2 divided by the damping rate of the oscillator. And again, when you're at the quantum limit, where is this coming from? Half of it is the imprecision noise, the intrinsic shot noise fluctuations of this current. Half of it is from the back action noise. Okay, so if you actually look at this total noise, that's plotted on the x-axis here, as a function of the optomechanical coupling, or equivalently of how strongly you're driving the cavity. The two different limits, so for very, very weak couplings or weak drives, this is that imprecision noise that really dominates the noise that you see, the fundamental fluctuations in this current here. For really large laser powers, the back action kills you. When you actually match these two things to exactly be equal, that's when you reach this quantum limit. Okay? And so, again, what's an experiment you could do if you actually did reach this quantum limit? Well, one thing you could ask is, what if the mechanical resonator did start at 0 temperature? Okay, so without the coupling to the cavity, the mechanics is at 0 temperature. All I have are 0 point fluctuations. Could I actually measure that in this kind of experiment? Again, the answer is yes, but there's a constraint on how big is the signal-to-noise ratio you'd see. Okay, so this is really showing what you would see if you had an ideal experiment starting with the mechanical resonator at 0 temperature. Okay, so here is the 0 point fluctuation spectral density of the mechanical resonator. Okay, we're going to add in the back action noise. So we're going to pick a detector that really reaches the quantum limit at the mechanical resonance. It's going to add a quarter quantum of noise. So that's the orange curve here. And then when I add the imprecision noise, that's this white noise background, it moves everything up, an amount that also corresponds to a quarter quantum on resonance. Okay, so what's the upshot of this? If you want to do this continuous monitoring of the 0 point fluctuations, the absolute best you can hope for is a signal-to-noise ratio of a factor of 4. Okay, so this peak here is 4 times the noise background away from the resonance. Okay, so pretty much out of time, let me just jump to one last thing in a little, in the spirit of maybe Jeff's lectures, I should add a little bit of some kind of rant or something that peeves me when it comes to talking about the quantum limit. And something that peeves me is the term standard quantum limit, which is used in a completely non-standard way, and often in a way that doesn't really refer to any kind of quantum limit at all. And so when you see this term SQL, be very, very wary. I often think we should call it the so-called quantum limit. So often, what do people mean when they mean the standard quantum limit? Again, this is very common in the gravity wave detection community. What they mean is, again, here's our full, possibly nasty-looking expression for the added noise. What they mean is to say, well, imagine you had absolutely no back-action imprecision correlations. So imagine this term here was just 0, right? Then the best you could hope to do would just be to balance these two terms by picking the optimal value of A. Okay, and so when you do that, this is often referred to as the SQL. The bound you get on the minimum added noise, it looks like what we talked about before. Hey, look, there's an H bar, that's good. But it involves the magnitude of this susceptibility. So what's the actual quantum limit? The imaginary part of the susceptibility. Okay, so on resonance, those two things, not different at all. Because on resonance, that force noise susceptibility is perfectly imaginary. Away from resonance, there's a huge difference between those two things. And just to give you an example, just ignore the rest of the things on this slide. What's shown here is the added position noise as a function of frequency. And again, 0 here is mechanical resonance. We're moving away from mechanical resonance. And I'm normalizing it compared to the 0 point spectral density. Okay? So the quantum limit here, the real quantum limit, no S, is this 1 here. The minimum added noise in every frequency is the 0 point noise. Okay? This so-called quantum limit, if you ignore correlations, yeah, you perfectly reach the true quantum limit on resonance. But now if you're interested in actually minimizing the added noise away from resonance, that's this blue curve here, that's this SQL, you're huge factors away from the true quantum limit. Okay? So the upshot is the way that people normally use the term SQL, they often ignore the fact that correlations can help you. On resonance, that's fine. Correlations are needed. Away from resonance, that causes a huge mistake or amount of confusion. This standard quantum limit with no correlations is a huge factor larger than what the true Heisenberg bound on the added noise is. All right, and so I think with that, maybe as I'm already over time, I will stop. Hopefully I've given you a sense, maybe more than you ever wanted to know, about what the standard quantum limit is, or what the true quantum limit is, and where it comes from, but a rigorous sense of where it comes from and how you derive it. And with that, I'll stop. Thank you.